Hello guys. In today's video live stream, as I promised last time, we are going to solve paper 2 for IB/HL students. If you're an A-level student and working on grade B or C, you can also join in. It will be helpful, but this is like the oh no, I have to mute myself. Yes, but this paper mostly for IB/HL students. If you're SL student, you can also join. IB and A-level students working on grade B or C or lower. That's also fine. That will be helpful. Okay, well, let's start. So that's paper 2, open response questions, IB/HL. From Save My Exams, the link is below in the description if you want to solve it. So the open chain structure of sugar galactose is shown in figure 1 below. Okay, determine the empirical formula. Right, so empirical formula. First, let's find the molecular. Remember, empirical formula, it's the simplest whole number ratio of all atoms of all elements. So molecular formula would be, I just count all the atoms. 1, 2, 3, 4, 5, 6. So that's C6. Then all hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. And 6. 1, 2, 3, 4, 5, 6 oxygens. That's molecular formula. To convert it to empirical, we have to cancel out 6, 12, and 6 to get whole number, simplest whole number ratio. So I would cancel everything out by 6. So 6 over 6 is 1, so it's C1. 1 I don't have to write. H12 over 6 is 2. O1. 6 over 6. Then calculate the percentage composition by mass of galactose. Usually they ask this question in reverse, so usually they would give you the percentage by mass and ask for the empirical formula. Well, this is the other way around. So let's find percentage of carbon. So to find the percentage by mass of carbon, we can assume that we have 1 mole of a substance, and then for 1 mole of a CH2O, you would have 1 mole of carbon because it's C1H12, right? So I mean H2. So 2 moles of carbon, 1 mole of carbon, sorry, 2 moles of hydrogen, 1 mole of oxygen. So I do 1, that's moles of carbon times molar mass of carbon from the periodic table, 12.01, divided by the total molar mass. Well, let's find it separately. So MR, it's 1 carbon, 12.01, plus 2 hydrogens times 101, right? That's hydrogen. Oxygen is 16. Plus 16. That would be what, 30.03, I think. 2.02 plus 16, yeah, that's 30.03. So basically what I'm doing, it's mass of carbon, yeah, moles times relative atomic mass, divided by mass of the whole thing. If it's 1 mole, then the mass would be 30.03, and times 100%. So 39.99 or 40.0%. Then I do the same for hydrogen. So we have 2 moles of hydrogens per each mole of the empirical formula, divided by the total times 100 divided by, remember for IB you have to write molar masses to 2 decimal places just like they are in the periodic table. So 6.73%. And for oxygen, you can either subtract, do 100 minus the rest, or just calculate how I did it before. So it's 1 oxygen times 16 over 30.03 times 100, which is 53.3. Well, 28, well, approximately, yes, approximately, that would give you, the sum would give you 100%. Right, and formulate the balanced equation for the complete combustion of galactose. To make it 100, we can just put it as 6.7. Would it be 100? Yes, I think it would. Let's double check. 40 plus 6.7 plus 53.3. Yeah, that's 100 then. Next one, formulate the balanced equation for the complete combustion of galactose. For the complete combustion of galactose, obviously we have to use the molecular formula, right? So molecular formula, luckily we calculated, so C6H12O6. What is the complete combustion? Complete combustion is reaction with oxygen. So plus O2, oxygen is always O2, remember? And the products of combustion you need to know. So if it's an organic compound containing CH or CH and O, when it burns you would form CO2 and H2O as the products of complete combustion. Anything, if it was an alcohol or something, anything that has CH and O atoms would give you these products upon complete combustion. For incomplete combustion you'd get CO and water or carbon and water. Yeah, so water is always formed, and then the carbon product would depend on the whether it's complete combustion or incomplete. And we have to balance it. Right, so let's balance it in the order CHO. Usually that's the easiest order to balance combustion reactions. So I have 6 carbons on the left, 1 on the right. So I put a 6 here, then hydrogen, 12 on the left, 2 on the right. So to make it 12, I put a 6. Then oxygen, so on the right side I have 12 from here, yeah, 6 times 2, plus 6, which is 18. And on the left side I already have 6 here, so I don't want to change the coefficient in front of the fructose or galactose. And okay, so I need to have 18. I already have 6, and then I have to multiply 2 by something to make it 18. Yes, so something times 2 to make it 18. Well, that something is what is 6, right? So 6 plus 12 equals to 18. I hope that makes sense. Okay, next question. Lactose is a disaccharide sugar made from galactose and glucose unit joined together. A number of people suffer from lactose intolerance. Where's the question? How many molecules of lactose is enough to cause symptoms? I mean, these questions are so funny. Imagine you're in the exam and they give you this irrelevant information about lactose intolerance. That's in A level you can have a whole chunk of text which is completely irrelevant. All right, so we have question: how many molecules of lactose is enough to cause symptoms? And we know that we can tolerate 12 grams of C12H22. Okay, so we know the mass is 12 grams. What do we need? We need to find the number of molecules. Yeah, how many molecules? Well, to find the molecules, we first have to find the mole, so I do mass over mR. Okay, so 12 over 12 carbons. So 12 times 12.01 plus 22 hydrogens. 22 times 1.01 plus, that's an 11, plus 11 oxygens. Oh no, my G went. Okay, and then 11 oxygen, so 11 times 16. That's the moles. 12 over 12 times 12.01 plus 22 times 1.01. 16.00, by the way, yeah. That's 0.035. I would keep it to 2 significant figures because this is given me the mass is to 2 significant, so I'll just keep it like that. So that's how many moles of lactose we have in 12 grams, and then I convert it to the number of molecules. So if I know the number of moles of particles, I just multiply that by Avogadro's constant. So that times 6.02, I just multiply the calculator value, times 10 to the 23, so that's 2.1 times 10 to the 22nd molecules. Okay, let me check if this stream is going well. Let's see. Yes, okay. I think it's fine. Right. Next one. Next question. Carvone is an organic compound containing carbon, hydrogen, and oxygen. Okay. Carbon, hydrogen, and oxygen. Complete combustion of 0.1526 grams of carbon produces 0.447 grams of carbon dioxide and that amount of 0.1281 grams of water. Determine the empirical formula showing your working. Okay, so with this question, this space is definitely not enough, and usually it should be 4 marks. This question, is, by the way, is also in A levels sometimes, and most of the times people don't know how to solve it. So you can, even if you're A level, pay attention to this question, okay? Right. Well, let me copy this maybe. Yeah. So let me copy this and I'll explain how to solve it. So this is a type of question when they combust an organic substance and they give you the mass of CO2 and H2O, and you have to work out empirical formula from there. Okay, I think that's good enough. Yeah, that's fine. Right, how do we solve it? So what we have to understand is that this substance, carbone, it contains only carbon atoms, we don't know how many, hydrogen, and oxygen. And when we combust it, so it's a reaction with oxygen, we produce only CO2 and H2O. So you see all the carbon from that substance, it goes into CO2, and all the hydrogen goes into water. Right, so the number of carbon atoms, if it will be balanced, right, obviously, and the number of carbon atoms on the left equals to the number of carbon atoms on the right. So it means that the moles of carbon atoms on the left would equal to the moles of carbon on the right. And because we only have carbon in carbone, in that organic compound, we know that all of that carbon goes into CO2. So if we find the moles of carbon in CO2, it would be the same as the moles of carbon in this substance. And same we can do with hydrogen, but the ratio would be y to 2, yeah, not x to 1 as it's here. But we also understand that all the hydrogen from this substance, it goes into water, right? So if we find the number of moles of hydrogen from water, it would be the same as the number of moles of hydrogen in the substance. Can we do the same for oxygen? No, because this oxygen, yes, it was transferred to CO2 and H2O, but we added extra, right? So you cannot say that the number of moles of oxygen is the same as the number of moles of oxygen in CO2 and H2O. Okay, I hope that's fine. If it's not clear, you can ask me and I will explain again. I hope it's fine. Right, so what are we doing? So, okay, so my goal is to find the moles of carbon atoms, the moles of hydrogen atoms, the moles of oxygen atoms, and take the ratio. That's what I want to do. If I know the ratio, I know the empirical formula. Well, first, I start off by finding the moles of CO2. So it's mass over mR. So, that's 0.4470 grams divided by mR of CO2, 12.01 plus 16 times 2. Yeah, so that's 44.01, that one. I think by the end of this syllabus you will memorize this molar mass, which is 0.01016 moles. And that's the moles of CO2. Now we find the moles of carbon atoms, right? So the moles of carbon are in 1-to-1 ratio with CO2. So if you have 1 mole of CO2, you have 1 mole of carbon atoms. So it means that the moles of carbon atoms, it's the same as the moles of CO2. Then second, moles of H2O. Moles of H2O, again, mass over mR. So we have 0.1281 grams of water divided by molar mass, so 2 times 1.01 plus 16, which is 18.02. 18.02, which is 7.109 times 10 to the negative 3 moles. That's moles of water, and we want to find the moles of hydrogen. So water is H2O, right? Which means that per each mole of water, you would have 2 moles of hydrogen. You can think about it as if you have 1 molecule of water, you have 2 H atoms there. So if you have 1 mole of water, you would have twice as much hydrogens. So moles of hydrogen would be that moles of water times 2. Yeah, because it's H2O. Okay, so that is 0.01422. And let's highlight. So this I would need for the ratio. Yeah, this I would need for the ratio. And I only have oxygen left, so I don't know oxygen. Let's find oxygen. How do we find oxygen? Well, we already discussed that we cannot do the same, yeah, for oxygen as we did for C and H, because we added extra oxygen, so we don't know how much we added. And but what do we know? We know the total mass. Yeah, so you see they gave us the total mass of carbon. And what is this total mass? Well, this total mass, it's the sum of the atoms. It's number of carbon atoms plus hydrogen plus oxygen. So I already know the moles of C and H, so I can find the mass of carbon and hydrogen atoms and then subtract. Yeah, so then I would do 0.1526 minus mass of carbon minus mass of hydrogen, and what's left is oxygen. That's it. Yeah, so let's find the mass of carbon atoms. That's moles of carbon times relative atomic mass. So 0.01016 times 12.01 times, you see why it should be 4 marks at least, I'd say 0.1220 grams. And if we mess up somewhere, we will see it at the end, because the ratio would not be whole number ratio, it would be a mess, and then we'd have to check, but I hope we will not mess it up. Right, and then we find the mass of hydrogen, so that's again moles of hydrogen times relative atomic mass of hydrogen atoms. Yeah, not H2, it's atoms. So 0.01422 times 1.01, 0.014 times 101, so that is 0.01436 grams, and then we subtract then the mass of oxygen, so it's total mass, which is 0.1526. 0.1526 minus carbon minus hydrogen. All right, 0.1526 minus 0.122 minus 0.01436, which is 0.01624 grams. I hope that is correct. Next, so that's mass of oxygen. Then we do moles of oxygen. It's mass of oxygen over relative atomic mass over 16, which is 1.015 times 10 to the negative 3 moles, and then that's the final number we need for the ratio. And now we'll know whether we solved it correctly or not. Okay, then we take the ratio moles of carbon to hydrogen to oxygen, and literally if it's 3 marks they expect it to be around 3-4 minutes, so I'm not sure how that's supposed to work. I think you just have to save time on other questions. So 0.01016 to 0.01422 and to 1.015. That's our ratio, and then we divide by the smallest number, so by this one. Yeah. So then I do 0.01016 divided by that 1015, which is 10. Yay. Okay, so 10 looks good. If it's a whole number, looks good. Of course, it's possible that it wouldn't be the whole number from the very start. Yeah, so maybe you'd have to divide it again, but 10 looks good. And then I do this number 0.01422 over that 0.1422 over 1015, which is 14. Yes, and to 1. Yeah, so that's our empirical formula. Looks good. We got whole numbers. If we got something like 10.7 to 14.2, that would be a mess. Yeah, then we know that we solved it wrong. Well, okay, so that's C10 H14O. That's our empirical formula. Um, yes, empirical formula. Just keeping an eye on the stream if it's working. Empirical formula. Well, yeah, and that's how much space they gave you. Here, yeah, doesn't would not fit. Next. So this is solved, yeah, this is solved. Then 0.146 gram sample of carbon when vaporized had a volume of 0.0341 dm cubed at 150 Celsius and 100.2 kPa. Calculated smolar mass showing you're working. Okay, well, obviously that's PV equals to nRT expression, right? So we know the mass from information about volume, temperature, and pressure. We can find the moles, and then we can find the molar mass. So remember, if moles it's m over mr, then mr would be mass over mole. So we know the mass. Now we'll find the moles from PV equals to nRT. nRT, so I rearrange PV equals to nRT, ideal gas expression, so it's pressure times volume over RT. And okay, now for IB, it's okay to plug in pressure and volume as they are here. So you can use volume in dm cubed, pressure in kilopascals. For A level, you can never do that. So for A level, you have to use cubic meters and pascals always, okay? For some reason, A levels doesn't allow you to use dm cubed and kPa. It's some convention, I don't know. But the answer would be the same, but still they might check whether you use dm cubed or meters cubed, and I lost the mark myself like this a few years ago. Okay, so, but for IB, it's fine. So I would use dm cubed with kilopascals. So you either use for IB, either dm cubed and kilopascals or meters cubed and pascals. So I just plug that in as it's written. Over R, it's the gas constant 8.31, and temperature must be in Kelvin. So 150 Celsius. Remember, to convert to kelvins, it's 150 plus 273, which is 423 kelvins. And then I calculate 100.2 times 0.0034, 1 over 831. So that is 9.72 times 10 to the negative 4 moles. Okay, so we found the moles from the data, yeah, from the pressure, volume, and temperature, and now I can find MR. So it's mass 0.146 divided by the moles. 0.146 over that 10 to the negative 4, which is 150.2. Well, I'll just round it to 150. That's a good molar mass. Yeah, it's not too small, not too large. If you got something like 15, well, probably it's wrong. If you got something like 1,500, probably you messed up the units. Yeah. Okay, so that's the MR. And then use your answer to part B, using your answer to part B, determine the number of molecules in carbon in 0.146 grams. Okay, I actually expected to calculate the MR, but okay. Well, right, so they said use it to calculate the number of molecules. I think we already know the number of moles here. Yeah, from B, yeah, we already, from B, yes. So we already know the number of moles, so to calculate the number of molecules, we just multiply that by Avogadro's constant. Times Avogadro's constant. And that's it. 10 to the negative 4 times 6.02 times 10 to the 23rd, which is 5.85 times 10 to the power of 20 molecules. Okay, yes, that was the question. Let's see how, yeah, we have a few minutes left. Maybe we start the next question, but then I will continue with this paper next time until we finish it. Right, so for each of the molecules below, draw the Lewis electron dot structure and use the valence shell electron pair repulsion theory to predict the shape of each molecule. Okay, so just Lewis structures and the shapes. Yes, let's see. Well, let's start. Oxygen difluoride. OF2. Okay, remember, I'll remind you how we do the Lewis structures. So to find the Lewis structure, we need to count the number of valence electrons. That's my method. You might use some other method. I'll explain you mine. Just, if you like it, you use it. If you don't like it, you can use some other method. So, am I in the, yeah. Oh, no. Sorry, guys. Okay. Does that work? Let's see. Yes, okay, that works. Right, so, okay, OF2, we find the number of valence electrons in the entire molecule. So oxygen is in group 16, which means that it has 6 valence electrons. Fluorine is in group 17, which means that it has 7 valence electrons. And that's what I write. So I do 1 oxygen plus 2 times 7. So it's 6 times 14, it's 20 electrons. And I like to convert it to pairs, right, to make it faster. So it's 10 pairs. So we have 10 pairs in the outer, in the outer shell of this, each atom of this molecule. So the total outer, total number of pairs in the outer shell of all atoms. Then I put oxygen in the middle. Usually the atom that is on its own, it's 1. Yeah, so 1 oxygen, 2 fluorine, so oxygen would be a central atom. And the first thing that I would do is I would attach fluorines with single bonds to oxygen. So I am attaching the side atoms to the central atom with single bonds. Okay. Then I will assign lone pairs on the side atoms so that each side atom has an octet. So you see, this fluorine has 1 bond. Octet is 4 pairs, right? This has 1 pair. So it means that it needs 3 lone pairs. So 1, 2, 3. Fluorine, this fluorine, it also has 1 pair now, so it needs 3 more. 3 more. Okay. What do we do next? Next we count how many pairs I have used up out of 10. So I have used up 1, 2, 3, 4, 5, 6, 7, 8. I have used up 8 out of 10, which means that the 2 extra, yeah, so 8 plus 2 is 10. So 2 pairs become lone pairs on oxygen. And you check it in this order, yeah, so that's your Lewis structure. You can draw it as dot and cross, you can draw it with lines, that's fine. For A level, be careful as well. For A level, they never ask for Lewis structures in A level, but they ask for dot and cross diagram, and they usually say only indicate the pairs that affect the structure. Yeah? So if you're doing A levels, you don't have to draw the octets on the side atoms because they don't affect the structure. But when you figure out how many lone pairs the oxygen has, then you still have to count them, just don't draw them, okay? So that's for IB, that's how it should work for IB, so that's a Lewis structure. And okay, now what do we need as well? We need the shape. Okay, how do we find the shape? So we have this table that everyone hates. This is the table for IBHL. And well, for SL you need it up to here. For HL you need the rest as well. So in this table you have the number of atoms bonded to the central atom and number of lone pairs on the central atom. So what do we have? We have oxygen, that's our central atom, and it has 2 atoms bonded to it and 2 lone pairs. So I choose, which line do I choose? So I have number of atoms bonded to the central atom is 2 and number of lone pairs is 2. So that's my shape. Yeah, so that's V-shaped, bend, and 105 or 104.5 predicted bond angle. Okay. We don't need the angle, so I just write V-shaped. So if you were to draw its shape, it would be like that. Yeah, and then 2 lone pairs, or just bent. And on fluorines, you also have lone pairs depending on, like if they say just show lone pairs that affect the structure, the shape, then it's these 2 on the central atom. But we don't have to do it because they asked for the Lewis structure only, so we don't have to draw the shape, we just have to name the shape. Next one, PF3. I'm doing the same thing, so I find the number of valence electrons. So phosphorus, where is phosphorus? Phosphorus is in group 15, so that's 5 valence electrons. Fluorine again 7, nothing changed here. So 5 from phosphorus plus 3 fluorines, so 3 times 7, 21 plus 5, 26 electrons, or 13 pairs. Phosphorus goes in the middle. Then I connect fluorines with single bonds. Then I put octets on the side atoms on fluorines. Each needs 3. And then I count how many out of 13 I have used up. I have used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of 13 are used up, which means that phosphorus has one lone pair, like that. And to find the shape, I go to the table. So phosphorus has 3 atoms bonded to the central atom, one lone pair. Okay, let's see. So 3 atoms bonded to the central atom, one lone pair, trigonal pyramidal shape, 107 degrees angle. Trigonal pyramidal. Right, and the last one, BCl3. Well, I'll just make another page. BCl3, we do the same, but in this one you need to know that boron is an exception, okay? So BCl3, let's see, boron is an exception in that way that it doesn't need an octet. It's stable with 3 pairs around it. It can form an octet, but it's stable without. It's stable with 3 pairs. Well, let's see. So if I go here, so boron has in group 13, so it has 3 valence electrons, and fluorine, was it fluorine? Chlorine. Chlorine has 7. So it's 3 plus 3 from boron, 3 times 7, so that's 21 plus 3 is what, 24 electrons or 12 pairs. I do the same, so boron in the middle, bonded to chlorines, then octets on chlorines, then count how many pairs I have used up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have used up 12 out of 12, which means that boron does not have a lone pair. But you see, this structure looks weird because normally in this case I would have to make a double bond. I would have to remove one lone pair, put a double bond to make boron an octet, but boron is an exception. It's stable just like that, and that's how we leave it. So then we find the shape. So central atom has 3 atoms bonded to it, 0 lone pairs. So go to the table, 3, 0, it's trigonal planar. The table obviously you don't have in the exam, you have to memorize it with the bond angles. Trigonal planar. Yes, okay. Well, our half an hour, 30 minutes are gone, so I'll stop here, but next time we can continue. Okay, yes, so I think, yes, next time we will continue with this. If you have any other topic requests, you can message me. I'll see what I can do. I'll see what I can do, and what I will try to do is I will try to run lessons in parallel with IB and to IB and A level students, but we'll see how much time I have. Okay, I'm off to marking. See you next time.